Hi, my name is Suwen, and thanks, Mark, for the introduction. So this is a collaborative work with Jingjie Zheng and Shumin Zhai from Google and my advisor, Xiaojun. In the modern post-PC computing era, a lot of times people need to interact with devices whose input and output areas are decoupled. For example, users use a separate touch surface, either a remote control or a game controller, to interact with the smart TV or their VR, AR headsets. Since text entry is essential for a lot of tasks, including searching and messaging, entering text is also a common activity in this scenario. However, the current way to support typing on these devices is very slow and unnatural. For example, to type on a smart TV, the user first needs to invoke a keyboard, which occupies most of the screen space. Then users need to use the controller to move the cursor and select every letter on the keyboard. This process is very slow. Apart from that, users also need to constantly switch their attention between the remote display and the touchpad where they are typing. So we present i'sFree. i'sFree allows users to perform gesture typing on the touchpad without displaying the keyboard on the remote display or the touchpad. So users can imagine the keyboard on the touchpad, and our system can estimate the keyboard location and decode the output. So this is how it works. So users can perform i'sFree gesture typing and focus their attention on the remote display. We believe that i'sFree can be used in a lot of scenarios, for example, in your games when you're trying to type something, or when you are performing search on your TV. i'sFree also supports novice to expert transition. What this means is when users are unsure about how to type a word, we can simply pause their finger on the touchpad, and we can show a Qwerty layout on the remote display to guide the users. So why do we think gesture typing is better than tap typing for i'sFree interaction? First, gesture typing is error tolerant. It allows users to express their intended words by using approximate gesture shapes instead of precisely tapping on the individual letters. Second, the end of a gesture stroke can naturally work as word delimiter, so users don't have to enter the space key to end the word. And third, because i'sFree interaction is basically a recall-based interaction, pictorial effect can help shows that users are better at memorizing the shapes. So gesture typing actually enables this interaction. Although gesture typing has a lot of potential, supporting it in an i'sFree manner will be difficult, because users could draw the gesture anywhere on the touchpad without the visual guidance of a keyboard. The input signal could also be very noisy. So how to address these challenges will be the main focus of our project. For the rest of the talk, I'll be focusing on the following 3 points. First, we want to understand how users perform i'sFree gesture typing. And second, how it helps us design our i'sFree decoder. And third, I will present a formal evaluation of the i'sFree system. So to understand how users perform i'sFree gesture typing, we conducted a user study with 12 users. We used Nexus 5X to simulate the touchpad, so the screen on the device is turned off. User cannot see anything on the touchpad. On the remote display, we show 40 phrases randomly selected from the Mackenzie phrase set, and no Qwerty layout is shown on the remote display. So users were asked to gesture type the phrases. After we collect the user's input gestures, we first want to analyze where users imagine the key positions. So we use the dynamic time warping method and translate every gesture into the individual key positions. So this figure shows what the imaginary key distribution is. The black boundary around the layout is the actual size of a touchpad. So we can see that the distribution follows a Gaussian distribution, but the variance in the y direction is much larger than the x direction. So based on our observation from the study, we believe that the left and right edges of the touchpad can help user locate the horizontal position of the keyboard, but not the vertical position. So the unknown vertical keyboard location contribute to the large ambiguity we observe in the y direction. To verify our assumption, we propose a normalization procedure. So what the normalization does is we assume there is a keyboard located at the bottom of the touchpad, and we translate every gesture onto the same keyboard. So this translation doesn't change the shape or the size of the gesture, only its vertical location. The right figure shows the distribution after we perform normalization. We can see that we are able to reduce the vertical variance by over 50%. So this confirms that normalizing the keyboard location can help reduce the variance in the input signals. We also noticed that the size of the imaginary keyboard is very similar to a virtual keyboard on the Android device. We believe that users' daily typing experience largely contribute to this behavior. Although there is a large variance across different words for the users, we also noticed that from 2 consecutive gestures within a trial, the keyboard position is actually very similar. So what I mean is when we take 2 consecutive gestures user draw and analyze the vertical position of their imaginary keyboard, the vertical offset is actually very small. So when users perform EyesFree gesture typing, they tend to keep their hand position, and therefore the vertical position of the keyboard relatively stable across from word to word. So after understanding how users perform EyesFree gesture typing, we are going to design the EyesFree decoder. Before I start, a quick overview of how a general gesture typing decoder works. It takes the input gesture and passes it to the spatial model. The spatial model will compare the input gesture with the perfect gesture template, which is connecting the key center of every letter in the word. We combine the spatial score with the language score from the language model and get an ordered list of candidate words. Users can select from the list one final output. So why does the general gesture typing decoder won't work for EyesFree gesture typing? Remember we said users can draw gesture anywhere on the touchpad. So for general gesture decoder, without knowing the keyboard location, the spatial model won't work properly. So that's how we design our EyesFree gesture decoder. We built it on top of a general gesture typing decoder with a new module called the Keyboard Vertical Location Learner. This module will learn the keyboard vertical location from the current input gesture and the previous output. Combining these 2 components, we can supply the spatial model the final estimation of the keyboard location. And the gesture decoder can work as expected. So how does these 2 components work? The first component is the geometric component. It's based on a simple intuition that the gesture trace should not exceed the boundary of the keyboard. So when we have a gesture stroke, we can find the highest keyboard location based on its shape and size, and the lowest possible keyboard location. Any keyboard within this range is also considered possible. So the second component is called a historical component. The historical component learns the keyboard location from the previous output word. So when user draws this gesture and selects an output word, in this case, user selects good as the output, we can know for sure that this will be the keyboard location. And since we noticed that there's only a small offset from word to word within a trial, we can allow a small offset from the current keyboard location and get an updated estimation of the keyboard location. Then we combine these two components and take the intersection of the two components' result and get a final estimation of the keyboard locations. We assume every keyword is equally possible within this range. So we use the Monte Carlo method. Basically, we take n possible keyboard location from this range, calculate their spatial score separately, and take the average as the final spatial score. So next, I'm going to show you how we evaluate i'sFree. We conducted another user study with 18 users. The first condition is i'sFree. We use our i'sFree gesture decoder, and users can basically type anywhere on the touchpad. On the remote display, by default, we don't show the QWERTY layout. We also implemented the training wheel, so when users pause their finger on the touchpad, we will show the QWERTY layout to help them type. We designed two baseline conditions. The first baseline condition is called isound gesture typing. So in this condition, we assume there is a keyboard located at the bottom of the touchpad, and we use a general gesture typing decoder. We show both the QWERTY layout and the gesture trace on the remote display. The third condition is called i'sFree baseline. It's similar to the isound gesture typing condition. We use a general gesture typing decoder, but we don't show the gesture trace or the QWERTY layout on the remote display. We also implemented the training wheel so user can still see the keyboard pop up when they need it. So let's see some of the results. In terms of input speed, users can reach 23 words per minute on i'sFree, which is about 50% improvement over the baseline conditions. We believe two factors contribute to the performance. First, users are able to focus their visual attention on the remote display, which helps them typing. Second, our keyboard vertical location learner can effectively learn the keyboard locations, so users make less errors and therefore less error corrections. Then in terms of error rate, the error rate on i'sFree is about 2.1%, which is significantly lower than the baseline conditions. So to sum up, we believe that i'sFree gesture typing is a promising input method for remote control interaction. Gesture typing in general is also very suitable for remote interactions beyond the remote control scenario. Second, by estimating the keyboard vertical location from the current input gesture and the previous input gesture, we are able to improve the typing speed by 46%. So overall, we believe this input method can be used in a lot of scenarios beyond TV and remote control. For example, you can use it on your game consoles or your VR, AR headsets. And before I end my talk, I'd like to run a little ad that I will be graduating this year and looking for possible opportunities. And thank you.
Thank you. Hello, my name is Knut Park, and I'm from KAIST. Thank you for the great presentation. I have actually 2 questions. So, first one is effect of the posture. So, as I see from the video, all the performers hold the smartphone with one hand and draw a gesture with the other hand. So, did you ever look what happens if a user uses your prototype with only one hand and draws gestures with a thumb? So, can I use your prototype in that way? And actually, I have one more question. Mm-hmm. The second one is, how can we type a single letter word with your prototype?
Okay.
Yeah.
So we didn't distinguish the postures user use, but we allow user to select whatever posture they like. So some user did use one hand to hold the phone and just type with their thumb. So we didn't distinguish between the 2 postures, but we can actually, in the future, we can see how the posture affects their touch point distribution and how we can decode them. And second, in terms of single letter words, so user can just tap on the vicinity of the region. So most commonly, single letter words are A and I, so they can just type on the vicinity and they can input the single letters.
Okay, thank you.